Okay, so we're going to begin chapter 6. And to borrow a concept from baseball, we're going to do the old wind-up. And the wind-up here, is the preparation before the pitch. And the pitch here is going to be our discussion on photosynthesis and on metabolism. Okay, so central question here. So the central question here is, how do we go from things like pixie sticks and hamburgers, how do we go from these things to that of motion? Okay, how do we get there? And another topic is, how do we get from things like the sun over here, how do we get from the sun to things like hamburgers and our beloved pixie sticks? How do we do that? Well, that's really the central idea of this chapter, and not these chapter, but this section of the course. This part is going to be really important, something called photosynthesis. Okay, photosynthesis. We're going to take the energy in the sun and we're going to convert that into molecules. Through metabolism, we're going to take those molecules and break them down and use those for energy. Now, you may be sitting there right now and thinking, this doesn't apply to me. I am sitting perfectly still. I'm just watching some video. How does this apply to me? Well, internally, your muscles are in motion. And that motion of energy is what we call kinetic energy. You're in motion right now. Your heart is beating about 60 to 80 times per minute, depending on your activity. Okay, it can go less with your resting heart rate. But suffice to say, your heart is beating. There's muscles around your veins that help propel your blood forward. Because as your blood goes through your circulatory system, it's going to lose blood pressure. So you have to use muscles to propel that blood forward. Your diaphragm is contracting, and when it contracts, it allows you to breathe in. Okay, so, you're doing this all the time. You might not perceive it, but you are doing it. Now, these are really two forms of energy. This is what we call a potential form of energy. I'm going to say PE. Our foods are potential energy. Okay, they're not moving. There's energy due to their state. Your heart moving, energy of motion, we would think of as kinetic energy, the energy of motion. Which brings us to our next topic. So there's two forms of energy. We have our potential energy. Potential energy has the energy to make things happen. It's an energy of position or of state. So for example, a hamburger has chemical potential energy. Pixie sticks have chemical potential energy. Any food would have some type of potential energy, and that is a chemical form of that potential energy. Kinetic energy, on the other hand, is the energy of motion. Your heart beating, for example, that has some kinetic energy. Your diaphragm, as it moves and allows you to breathe in, as it relaxes and it moves up and you breathe out. Okay, all of these have kinetic energy. So two forms of energy. And you might start thinking, well, this is a biology class, not a chemistry class, and certainly not a physics class. But the reason that we discuss this in biology is, again, these biological examples. Your heart beating. How do we cause your heart to beat? How does your diaphragm move? This all takes the big E, energy. Right? How do we get this energy? Ultimately, the ultimate source of energy, and a very important concept we're going to get to later, the ultimate source of energy is the sun. This is the ultimate source of energy. More on that later on. Now, chemical energy is a type of potential energy. Okay, we've already talked about a few examples of this, right? Foods are a type of chemical potential energy. It has the capacity to do some form of work. Now, there's an interconversion between these forms, right? Think about you eating food and then you doing some type of work. This conversion, okay, right here, this conversion is going to be very important when we start talking about metabolism. Why is it that you can bring food in and convert that food into the energy of motion? Or why is it you can have carbohydrates in the morning and then later on go for a long run in the afternoon? There has to be some type of what? Conversion going on, right? Something in our bodies is taking that chemical energy, your spaghetti, your power bars, what have you, and it's converting that chemical energy into kinetic energy, your muscles moving, right? Propelling you forward as you run. That is essentially going to be due to your metabolism and what we call cellular respiration. And again, that's a topic in soon to be reviewed chapters. Now, the first law of thermodynamics basically is that energy is neither created or destroyed. Okay, you can't create or destroy energy. You can't just poof, it's here and poof, it's gone. Okay, it can only be transferred from one form to another form. There's only a transfer that happens. So which is to say, whatever energy you put into a reaction, the same amount of energy will come out of a reaction. Now you might say, well, if that's true, then why can't we have perpetual motion machines, right? Why don't perpetual motion machines work? Why is it that I can't, if I push something on the ground, so we have something like here, this is the ground right here, and I push something on the ground and I impart energy onto something, why can't that thing just keep on going? And the reason is that this whole total energy out, think about this, as something's being propelled forward, you know, you're going to have air resistance, you're going to have friction, right? So there's going to be different ways that energy can be transferred from the system. It doesn't all have to go into motion, for instance. Now, not all energy is of equal forms, okay, or of equal concentrations. Some energy is very highly concentrated. Okay, for example, gasoline is a highly concentrated form of energy, right? Think about that gallon of gasoline. Very concentrated energy form. Your battery in your cell phone, very highly concentrated form of energy. Sugar, for instance, right? Another highly concentrated, organized form of energy. Now, other forms of energy can be what you might think of as lower quality, okay, which are more disorganized, or more importantly, they're not as concentrated, okay? Think about heat and sound. We can't really, those are not very easy to use when you think about it, right? It's hard to harness the power of sound for energy, right? So again, point I'm trying to get to here is not all energy is created in equal qualities. Okay, there's going to be some difference in that regard. Entropy. Now, we need to talk about entropy before we bring in the second law of thermodynamics. Okay, so entropy is the amount of disorder in a system. Okay, and this is going to increase spontaneously. It just happens spontaneously. You don't have to put energy into the system to make this happen. But to do the reverse, you have to add energy. Okay, this is going to become very important when we start talking about how life, as we form life, we become more ordered. We're going actually the opposite. And when we do that, we have to put energy into the system. Now, this discussion will become more important as we get into future chapters. But for now, we're just going to leave it with the idea of entropy is the amount of disorder in a system. And processes that increase entropy or disorder tend to happen spontaneously. And processes that decrease entropy or increase order in a system tend to require the input of energy to make that happen. Okay, so a new concept we're going to talk about is energy flow. Okay, how think about water coming down a mountain, right? Coming down a waterfall. How, if that water is energy, what pathway does that water take? Okay, the sun is the ultimate source of our energy. Okay, the energy that I'm using to talk to you right now. The energy that is powering your displays on your computer. The energy that's powering your cell phone. The energy that's heating and or cooling your house or your apartment. All of that energy, the energy that's causing your heart to beat, the energy that's causing your circulatory system to pump blood through your body, all of that energy, the energy the bacteria is utilizing right now to grow and is covering you, all of this ultimately comes from the sun, that large ball of hydrogen that's fusing into helium in the center of our solar system. That all comes from the sun. Now you might ask yourself, well, great, does that mean I can go outside and, hold my body up to the sun and make energy? And of course you can't. It doesn't work that way. We're not solar panels. All right, so how do we get energy from the sun, yet we can't derive energy from the sun directly? Well, the answer to that question comes in the form of looking at what we call the producers, also known as the plants. And the plants are going to take the energy of the sun and they're going to convert it into useful forms of energy that we can ultimately use. And we here are the consumers. Okay, consumers are humans, they are cows, they are bacteria, they are fungus, they are protozoans, they are almost all life. Okay, and we're going to get to the differences pretty soon. But the plants are going to take that sunlight and then convert that into a form of energy, a chemical potential energy, and that's transferred to the consumers. Now, why is this important? Because how it does that, how it takes the sunlight and converts that into a chemical form of energy, we talk about with the term photosynthesis. And break the term down, photo meaning light, and synthesis meaning to create. And in the truest sense of the word, that is exactly what's happening. It's using the energy of the sun to create a chemical potential energy. Okay, and that's basically what photosynthesis is all about. Now, that's a little bit more than what I'm letting on now, but that's a pretty good one-sentence description. Now, on Earth, energy flows through the producers, then to the consumers, meaning that here's the sun right here, okay? Here is our sun. The energy of the sun goes to the producers, the plants, okay? And the producers then let me say it this way, then we consume in some form or fashion. The producers or a consumer that has used the producers. That's a mouthful. What do I mean by that? Okay, you want energy now, right? Good. Do you go outside and hold yourself up to the sun and somehow absorb the energy like Superman? No, you don't. What do? Well, one thing you can do is you can go outside, you can eat an apple. Okay? You have just consumed one of the producers. Right? Exactly. Well, apples are fine and dandy, but what if you want something more than an apple? What if you want something like a steak? Okay? Well, are you eating a plant when you eat a steak? No, you're not. You're eating another consumer, right? Okay, so what happens there? Well, the cow that you get that steak from, the cow is going to eat the grass. Okay, as it eats the grass, it will then convert some of that energy into muscle and ultimately that protein, and then to muscle, and that's what steak is. So that cow will be a consumer. And then we will consume that consumer. So there's two ways we can get that energy from the plants, either from the producers, I should say. Either a direct retrieving of that energy, for example, through a fruit or a vegetable, or we can eat some type of other consumer that has obtained that from a producer. For example, we can eat cows to make hamburgers, for instance. Okay, so there's two ways that we can get that energy from the sun, neither of which includes directly getting it via the sun. We always have to either go through a producer directly or a consumer that has somehow in some form or fashion interacted with a producer. Okay, does that kind of make sense? Okay, so that's energy flow. Okay. Now, consumers will consume producers to obtain energy. Okay, very important idea. Consumers, us, will consume the producers to obtain energy. Now, does that mean that we can only obtain energy from the producers? Well, it depends on how you think about it. What we just talked about is being reiterated now. Consumers can directly interact with the producers. For example, a consumer, you, for instance, can get an apple. Okay, that's directly from a producer, and you can obtain energy from that. Okay, alternatively, you can consume a meat, for instance. Well, the meat comes from a cow, using this example, and that was a consumer. But where did it ultimately get its energy from? Well, you keep on backtracking it. The cow ate grass, right? The grass gets into the gut of the cow and it's broken down. A lot bacteria is really important in this breakdown. But ultimately, end of the day, what makes that energy? Well, on Earth, the producers, the plants make that right here. Okay? And what ultimately leads to that energy from the producers is the sun. Okay? So the sun is the ultimate source of energy. So you're sitting there, your heart's beating, whatever. All of that energy comes from the sun, because the sun was what allowed the producers to grow. Because the producers grow the plants, for instance, right? Vegetation allows that vegetation to grow. Then you as the consumer can take that plant material, and consume it for energy. Or you can consume another consumer for that energy. Okay, either way, this guy running right here, this guy running, the energy used for that ultimately comes from one source, and that is the sun. Now, different levels of consumers. As we said before, some consumers are themselves consumed. So that cow, for instance, that will make your hamburger, that cow is a consumer. Okay, this is a consumer. And we will consume its products. So we are a consumer of consumers. Does that make sense? Okay. We'll talk about levels of consumers later on, but right now we'll just say that there are different levels of consumers. And some consumers are themselves consumed. Okay, and cows are an excellent example of this. Now, as energy goes between producers and consumers, there is a loss of usable energy in the process. Now, you may throw your hand up in the air and say, whoa, 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 I don't get this. I thought you said that energy can't be created or destroyed. So how can you lose something if it can't be created or destroyed? Well, there's a difference between creating and destroying energy and a loss of usable energy, and I emphasize the term usable. Okay, not all energy is of the equal quality, right? And we said that before, that there's more concentrated forms and there's less concentrated forms, right? Gasoline and sugar, that's highly concentrated usable forms of energy. Heat, sound, those are less usable forms. They're not as high quality, if you will. And as we go between producers and consumers, we have a loss of this usable energy, meaning that the energy is going into other forms of energy that we cannot readily utilize. Okay, classical example is that of driving a car. Okay, you've got X amount of energy in that gas tank. In a gallon of gasoline, you got X amount of energy. Now, can you get all the energy out of that gas? So here's your car right here. You got 1 gallon of gas in it, and you can drive X amount of miles, right? Is there a complete transfer of energy from that gallon of gas to the motion of your car? And no, there's not. What happens? Where is there a loss of usable energy? Okay, well, if you've ever driven a car, open your engine up and feel the engine. What is it? It's hot, isn't it? So there's heat being generated, and a lot of that heat is lost to the atmosphere. I mean, that's why we have cool cars that have radiators, is it not? I mean, we have to cool the engine. It gets so hot in there because, it's making all of this heat that we can't readily recover, and it's not used in the motion of that vehicle. How about you listen to a car, and it goes, vroom, right? Someone has a big muffler on, and you can really hear it. That sound energy, guys, can we utilize that for motion? No, that is lost. That's another form of energy that we're not using to move that vehicle along. So the point here is that there is a loss of usable energy in this transfer. Energy is not created or destroyed, but it's not kept in that high. It is not. There is a loss of energy to less than high quality forms. For example, heat. Okay. Again, as we were saying, each conversion makes some energy unavailable. Okay, it goes into these more disorganized forms. Now, it does not break the first law of thermodynamics. The energy is not gone, right? It's not just poofed out of existence. It's not gone. Okay, it's just in a format that we can't readily use. Now, a gallon of gas has enough energy to move a 2,000-pound car about 150 miles. There's some variation on this number, but that's about how much you're going to get. But you can only move that car, say 30 or 40 miles. Because, as we said before, during that conversion, okay, you're going to have a conversion to other forms of energy. Now, you want the energy of motion. You want that energy in that gallon of gas to be converted to the kinetic energy, right? So you move your car along. But think of what else you have to do here. You have to, you're going to have sound. You're going to have heat. There's going to be wind resistance. All of these will take a toll, and all of these will be transfers of energy out of the system, okay? And because they're being transferred out of the system, they can't be used for this energy of motion. Now, every calorie of energy that we use comes from thousands of calories of sun energy. Very important idea here is that, you look at a hamburger, it has 500 calories of, it says 500 calories. Technically it's 500 kilocalories, but neither here nor there. You got 500 calories hamburger, right? Well, I'll tell you, the amount of energy used to make that 500 calories is many, 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 many times in excess of that 500 calorie hamburger. Because every time we transfer between different levels, there is a loss of usable energy. It's lost to other forms. Okay, so here is just an example. These are not like strict numbers, just to give you an example. Sun to the plant. Here is our primary producer. Okay? 1,000 calories of that sun energy goes in, and it makes 500 calories of plant material. All right? The plant is digested by the cow. 500 calories of that plant material go into the cow, and maybe 50 calories of meat come out. And then going from cow to human, a consumer to another consumer, 50 calories goes in, and maybe 5 calories come out. Now, these are just rough numbers. They're not meant to be like, oh, it's exactly this or that. It varies. But what I'm trying to impart here is that there is a loss in the transfer of energy. When you compare the energy in the sun, 1,000 calories here, and you compare that to what we derive from it over here, it is far less. And the reason is because in the transfer, there is a loss of high quality energy that continues on to the next level. Okay. Point is, energy does not equal the energy that goes in does not equal the energy that comes out. Now, different numbers on this, and this is just a rule of thumb. It varies, but about 10% of the energy in food is transferred to the next level. Okay, that's an approximate point. You'll have a lab on this later this semester, but that's an approximation. Okay, that there's about a 10% transfer of usable energy to the next level. Or next trophic level. Okay, and finally here, the energy we use is much, much more energy than we get from the sun. Which is to say, the sun provides, and the sun is being here, right? The sun provides a massive, massive amount of energy. Let's draw it with a box right here. It produces and provides a massive amount of energy, of which we use a small fraction of it. Okay? And that is due to that loss at each transfer. we need to replenish our energy on a continuous basis. Which is to say, no more sun, no more life. Now, luckily, our sun will last for billions of years, and we're not too worried about it running out of hydrogen anytime soon. What we should be more concerned about is the expansion of the sun, as it over time, ultimately, it may actually envelop Earth. But we're not terribly worried about the sun stopping all fusion. But what we do worry about is what would happen if some disaster were to block the sun from reaching the surface of the Earth. Now, think about the dinosaurs. There are some different theories on this. One theory has that there was a volcanic eruption and that introduced particulate matter into the atmosphere that blocked the sun from getting through significantly, and that ultimately led to the dinosaurs' extinction. Another one you've, I'm sure, heard of is an asteroid hit Earth. Same action. It put up a lot of material into the atmosphere, blocked the sun. Some little small mammals that were our kissing cousins then took the mantle and continued on, and here we are, among other theories. But the point is, when we block the sun, or when there is an interference with the sun coming and to the surface of the Earth, we have a problem. Okay, we need that energy from the sun. Okay, it has what is the sun provides is quickly lost. We have to have a continuous replenishment of that material, of that energy from the sun.